Now, in finishing out our circuit, we need to know whether this circuit is under, over, or critically damped. As we examine the circuit here, recall that what we were after was the voltage across this capacitor. And in finding whether something is over, under, or critically damped, we need to look at the resonant frequency and the dampening coefficient. And the resonant frequency is 1 over the square root of L times C, and our resonant frequency is the effective resistance of the circuit divided by 2L. So it's rather straightforward here because we only have one capacitor and one inductor, but our R parameter we need to examine in a little bit more detail because there are multiple resistors in the circuit. So what we want to do is find the equivalent version of the circuit and look at what is actually the effective resistance across this capacitor. And to do that, we're going to just redraw the circuit, only really focusing on the resistors. So here's the 6 ohm resistor, and over here we had a 4 and then a 2, and we'll turn off our voltage and current sources. So from the perspective of our capacitor, it is in parallel with a 6 ohm resistor, and also in parallel with the 4 and 2 ohm resistors that are in series with themselves, but in parallel with the overall capacitor. So our R value for here would be our 6 ohms in parallel with 6 ohms, which would effectively be 3 ohms. So our R for this value is going to be 3. From our previous slides, we saw that C was 8 millifarads and L was 0.2 henries. And so now we have enough information to calculate our resonant frequency and dampening parameters. And so alpha is going to be 3 divided by 2 times 0.2, which provides us a value of 7.5, and omega naught is going to be 1 over the square root of 0.2 times 8 milli, so 8 times 10 to the negative 3, and gives us a value of 25. Now, from here, we know that the resonant frequency is now greater than the dampening coefficient, so that means that our circuit is underdamped. And because our circuit is underdamped, we now have to go look at our set of equations for being underdamped and determine what. Now, returning to our sheet where we have all of our equations, we just found that our solution is underdamped. And so now we need to look at this form of the voltage across the capacitor and see all the parameters that we need to calculate. First parameter is that we need to know D1, which is the initial voltage across the capacitor, minus the final voltage across the capacitor. And it's important to note that at this time, that means at the plus mark, so the voltage at time 0 plus. We also need to know this D2 parameter, which is a long expression involving the initial currents across the capacitor and the voltages across the capacitor. And because our solution is underdamped, there's a special omega term that goes into all this calculation. And this omega term is the damped frequency, because the circuit sort of oscillates itself but not at its natural frequency. And that is the original resonant frequency squared minus the dampening coefficient squared, and then the square root of all of that loveliness. So if you were going to finalize out this expression, you would need to take V of C and calculate all these parameters and plug them all in, and basically just from this point on, plug and chug. In general, like going for a problem, we'll have you do this a couple times. For something like an exam, I'll probably just have you come up with the coefficients because it's a lot of just mess to plug all these things in. But remember, for the style of circuit that you find, you need to determine whether it's over, critically, or underdamped. And from there, this chart right here will give you all the parameters that you need to calculate.